Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Okay, so as it names, the power divider, it will divide power. Okay, when the power must be split among multiple transistors in an amplifier, the antennas, or any other scenarios. So the power divider is the solution, okay, or the suitable devices to be used. So the power divider splits an input signal into two or more outputs that usually, but not always, equal in amplitude and phase. And a good power divider have the greatest port-to-port isolation. Isolation meaning that one port will not disturb the other port. Okay, for example, if the transmission is from port 1 to port 2, so there will be no signal traveling from port 2 to port 3. And a good power divider is also having lowest insertion loss and voltage standing wave ratio, VSW, lower insertion loss, and also VSWR, and least amplitude and phase imbalance over the entire frequency range of the device. Right, so the right hand figure shows how the simple power divider looks like. For example, this is three-port network. So the first port is the input port, and the port 2 and port 3 is are the output port. So input signal is divided into two or more output signals of lesser power. Okay, so for example, the input power is P1 or P in, so it will divide equally to port 2 and also port 3. Okay, so sometimes they could be imbalanced power divisions, in which port 2 may be given higher power if compared to the port 3, depending on the system requirement. Okay, in normal practice, so P2 and P3 will be having equal power division, which is usually half of the input power. Okay, this is also known as 3 dB power divider, in which half of the power is delivered to the output port. And the other term is the power combiner. So when two or more input signals combines at the output port. Okay, so you have separate input signal at port 1 and port 2, and these two signals will be combined and transmitted via a single transmission line. Okay, so in between these two ports there are resistor, okay, which be included to improve the isolation, to make sure that there's no signal traveling in between the adjacent ports. Okay, these are three main types of power divider. The first one is the simplest one, the T-junction. Right, so this is the simplest type of power divider in the shape of T, representing three transmission lines connected at a single point. Right, three transmission lines, 1, 2, and 3, connected at one point, and this power divider will divide the supplied input signal into two outputs that are equal in amplitude and phase. Okay, but sometimes the power may not be divided equally into port 2 and port 3, depending on the ratio or the requirement of the system. Right, the second one is the resistive power divider. It's more or less the same as the T-junction, but it is an improved version of the T-junction power divider, in which there is three resistors, okay, 1, 2, and 3, being included at each transmission line in order to improve the isolation. Okay, so it's simple. The design is simple but lossy due to the inclusion of the resistors. Okay, because there's usually power loss across the resistors as the resistors absorb power. So this will provide to higher insertion loss as well. And one of the disadvantages of resistive power divider, there's no port-to-port isolation. Okay, port-to-port isolation is not good for resistive power divider. And to improve further, there's an upgraded version of the T-Junction power divider, which is called Wilkinson power divider, in which it consists of two quarter wavelength transmission line with a load resistor to provide isolation. Okay, it must be lambda over 4 quarter wavelength of transmission line with load resistor to provide isolation. It's here inherently matched and reciprocal. You can remember the meaning of reciprocal when the metric S is equivalent to its transpose. What is transpose? So when the first row become the first column and the second row become the second column, and etc. And if you compare the transfer version to the original S matrix, so it will be similar. Okay, but the one of the disadvantages of Wilkinson power divider is it is not lossless. Okay, that's lossy due to the additional element included into the design. And one of the advantages of Wilkinson power divider, it can be configured as N-way. Okay, more than 2 ports can be included in the design. Okay, let's look at the first one, the simplest power divider design, which is the T-Junction. So it is a 3-port network, so the matrix will involve from S11 up to ST3. So if all the 3 ports are matched, so there's 0 reflection at port 1, port 2 and port 3, therefore S11, S22 and S23 will be equal to 0. Okay, if each of these are matched, in which the ZL is equal to Z0, the characteristic impedance for each line. Okay, for example, port 2 you have one transmission line, and port 1 you have the characteristic impedance equal to Z0. For example, port 2 you have Z1, here you have Z3. So if the Z load at each port match to the impedance of individual transmission line, then the system is matched. Okay, normally a power divider or combiner is a reciprocal network device. Okay, if it is reciprocal, so forward and reverse transmission line are the same. So S11 will be equal to S21, S13 equal to S31, and S23 will be equal to S32. Okay, okay, so if the system, the T-junction network, is matched and reciprocal, therefore the S matrix, okay, this matrix can be further reduced to this. Since it is matched, so S11 equal to S22 equal to S23 equal to 0, and then S12 equal to S21, okay, since it is reciprocal. Okay, next is the lossless power divider. Alright, so in general, this junction can provide an unequal power division. As I mentioned earlier, the power may be divided equally to port 2 and port 3. However, it can also be used for unequal power division between the output ports. right? And if you look at this is the input port, port 1. Okay, so when there's a discontinuity, okay, on the transmission line, so it will induce or introduce fringing fields at the edge of the discontinuity structure, and then this will lead to stored energy, and it can be estimated by lump susceptance given by JB. Okay, so in order for this divider to match to the input line, so the total impedance or the admittance must be equal to 1 over Z1 plus 1 over Z2 plus the susceptance must be equal to 1 over Z0. Or if Z1, Z2 plus the susceptance must be equal to the intrinsic impedance or the characteristic impedance of the transmission line. Okay, for lossy transmission line, okay, it is not lossless, so the JB will be included in the calculation. But for lossless transmission line, it is assumed that the susceptance value JB equal to 0. Therefore, the total admittance will be equal to 1 over Z0. However, in practice, the B is not negligible, okay, due to discontinuity and the stored energy on the susceptive components. Okay, so we need to use the matching network, okay, in order to cancel the susceptance. But this one can be is practical for narrow frequency range. Okay, let's look at an example. A lossless T-junction. Okay, lossless, so we can assume that the JB equal to 0. Alright, power divider has a source impedance of 50 ohm, so source of 50 ohm. So we can assume that Z0 for the input transmission line is 50 ohm. And then the question asks you to find Z1 and Z2 so that the input power is divided in a ratio of 1 to 2. Okay, meaning that this power divider doesn't provide equal power division to port 1 and port 2. Okay, so this is the input port, and the output port is port 1 and port 2. Okay, so in order to get the Z1 and Z2, we only know the input impedance at the input line, Z0 equal to 50 ohm. So we need to consider the information that we have in terms of the power division. Alright, so the total power given P in, we know that the power divider will divide the power to the output port, port 1 and port 2. However, the port 1 and port 2 being given the total power with the ratio of 1 to 2. Okay, so one part will be given to port 1 and the other two parts will be given to port 2. So in other words, port 1 will be receiving 1/3 of the power from P in, while port 2 will be given 2/3 of the power, the input power from the input power. Okay, once you have this equation, so you know that the power, to calculate power, P in, for example, it is equal to V0 over 2, the RMS, divided by Z0. Right, so V0 is the voltage across the port 1 transmission line. Alright, so same goes to port 2 and port 3. So P1, sorry, this is P in, so P1 is up here and P2 is there. So in which P1 will be depending on Z1 and P2 will be depending on Z2. Okay, once you have the P1 the equation for P in, P1 and P2. So you know that the relation between P1 and P2 as well to the P in. So then you can compare them. So you know P1 equal to V naught over 2 squared. So this is VRMS for port 1. So port 1, this is the supply voltage to port 1. So V naught over 2 squared over its impedance Z1, which is equal to 1/3 for P1. Port 1 receive 1/3 from P in. So 1/3, 1/3 of P in. So P in equal to V naught over Z2 squared over Z0. Therefore, your Z, so from here you can cancel out V naught, and then you can cancel this one. So you get Z1 equal to 3Z0, in which Z0 is equal to 50. So Z1 equal to 150 ohm. So same goes to P2, receive 2/3 from P in. So this is P2 equation, which is equal to 2/3 of P in. So you can simplify the equation. Okay, so P2 equal to 3Z0 over 2, which is equal to 75 ohm. Okay, usually when the power is delivered equally to the first port and the second port, so usually the impedance will be the same. For example, Z1 150, Z2 will be also equal to 150. Okay, but if it is not equally divided, so you will see that the impedance will be in different values. Okay, next the question asks you on to determine the reflection coefficient for each port. Okay, so let's begin for port 1. So for port 1, so to get the reflection coefficient here, so you'll see looking in from port 1, so looking from port 1, what you will see here, what will be the Z load, it's basically, so Z0 here is 50 ohm. Okay, what you will see at this point, you'll see that Z1 is in parallel to Z2, in which 150 in parallel to 75. So from here, this is your ZL. Okay, so reflection coefficient equal to ZL minus Z0 divided by ZL plus Z0 as usual. Okay, so from there you can get 150 in parallel to 75 ohm equal to 50. So your ZL equal to, this is port 1, gamma 1, so ZL1 50 ohm is the line impedance, right? So get the reflection coefficient. So ZL from the calculation equal to 50 ohm. So you get the gamma 1 or reflection coefficient at port 1 equal to 0, in which we can say that the port 1 or the transmission line 1 is in match condition. Okay, let's look at the port 2. Okay, view from port 2. So from port 2 is there. Okay, from port 2, so you'll see this gamma 2. So the line impedance for port 2 is Z1 equal to 150 ohm. So what will be the ZL at this point is Z0 in parallel to Z2. Okay, 50 in parallel to 75. So to get the gamma 2, Okay, the ZL minus the Z1, the line impedance, divided by ZL plus Z1. So ZL, in which 50, in this case 50 in parallel to Z2 is 75, so you get 30 ohm. So then calculate your gamma 2 or reflection coefficient at port 2. It is equal to 2/3. Okay, so it is not matched. Okay, if it is matched, so the ZL, the load impedance at this point, must be equal to 150 ohm, the individual transmission line. Okay, the internal or characteristic impedance of that particular lines. Alright, next for port 3. Okay, let's look at port 3. Okay, look at here. So from port 3, gamma 3, so what will be your ZL? So Z, the impedance equal to 75 ohm, the characteristic impedance of this line, of the third transmission line. So the ZL for this one, looking at this point, so will be Z1 in parallel to Z0. Okay, Z0 in parallel to Z1. So 50 in parallel to 150. Okay, so Z0 is 50, Z1 is 150, so you get 37.5, then get your gamma 3 equal to minus 1.3. Again, it is not matched. Okay, to get the system match, so you have to make sure that the ZL from each port equivalent to individual characteristic impedance of the lines, right? So then you can get the match system. Okay, next, in order to improve further the T-junction, so because it is difficult to get the 3 ports matched simultaneously, so the resistive divider is introduced. Okay, as mentioned here, the lossless, even the lossless T-junction divider suffers from the disadvantage of not being matched at all ports. Okay, so all ports cannot be matched simultaneously. So, and it does not provide isolation between the output ports, and it's difficult to achieve perfect isolation between the output port as well. So therefore, the resistive power divider is introduced, in which the junction is loaded by 3 resistors with a value of Z0/3 each, where all lines have the characteristic impedance of Z0. Okay, now the system is matched, so all lines will be having the same characteristic impedance of Z0. Okay, by introducing 3 resistors, for 1 resistor for each line, so 3 resistors for the whole network. So each of these resistors values of Z0/3. Okay, then the input impedance observed from the single transmission line, and also when you refer to the at each port of the transmission line, will be equal to Z0/3 plus 2Z0/3. For example, if you look at this point, Z1, okay, Z1 from here. So at this point, the Z load will be the ZL2, Z from port 2 in parallel to Z at port 3. So at this point, the Z load will be equal to the Z from port 2 in parallel to Z from port 3. Okay, so here is Z0/3. So the Z in will be equal to Z0 over 3 plus the ZL. Okay, so what is your ZL? So ZL from port 2 is this one plus Z0. Okay, Z0 over 3 plus Z0. Same goes to port 3. It is Z0 over 3 plus Z0. Oops. So in which you can say at this point is the 4Z0 over 3 in parallel, in which it is equal to 2Z0 over 3. So that's why the Z in here is equal to Z0 over 3 plus 2Z0 over 3, which is equal to Z0. So the system is matched. Alright, so the impedance Z at this point, as I mentioned, is equal to ZL here. So Z2 in parallel to Z3 equal to 4Z0 over 3. So the system is reciprocal. When you look at this point, Z2 for example, so it is Z0 over 3 plus Z over here. So in this case, the ZL from port 1 plus the ZL from port 3, which will be which yield the same value because all parameters are having the same values. So the resistive power divider can be matched at all ports, but even though it is not lossless, isolation still a problem for a resistive power divider. However, it improves the condition of T-junction, which all ports cannot be matched simultaneously. Okay, we have seen that the impedance for each ports of resistive power divider are equal to Z0, and all ports or all transmission line are in match condition. So let's look at how much power is delivered from the input point to the output port 1 and port 2. Okay, so the P in, so we know that we assume that the V at this point, at this junction is V. So the input voltage is V1. So V at this junction is equal to, you can use power divider. So here is your ZL. So ZL equal to your Z from port 1 in parallel to port 2, Z2. Okay, so it's equal to 2Z0 over 3. Right, so in this case, V across this junction equal to V1 multiplied with the ZL divided by the total impedance. So you get V equal to 2 over 3 V1. Okay, if you look at the input, okay, the total power in is 100% supposedly. However, the one delivered at this point is only 2/3 of V1. So V1 is the total voltage at the input point. So the total received at this point is only 2/3. It is not 3 over 3. It's only 2/3, meaning that 1/3 of the power is there's losses. Okay, it means there's attenuation of the power across the resistor. Okay, now let's look at what happened to the power delivered to the output port. Okay, so what will be the power received at port 2 and port 3? So now the input at this junction is V. So this part can be simplified by this. So here is your Z0, and here is Z0 over 3. Okay, so what will be your V2 across here? Okay, so the supplied voltage is V. So again, you can use the power divider. V2 equal to V multiplied with Z naught, in this case at port 2, divided by the total impedance. Okay, so what is V? So V from the earlier calculation equal to 2 over 3 V1. Okay, therefore the V2 is equal to half V1. Okay, so from 2/3 at this point, okay, and V1 supposedly 100%, and then another half being delivered to port 2, and it same goes to port 3. Okay, because both having the same total impedance. Okay, so that the power is divided equally to both port 2 and port 3. And so here you know that the power at the output port S12 S21 is equal to 0.5 or 1 over 2. So the S matrix can be listed as, so this is S11, so the system is matched, so S11 equal to S22 equal to S33 equal to 0, and S12 equal to S21 equal to 1 over 2. Okay, because the system is reciprocal. So the metric can be further simplified to this. Okay, let's look at in terms of the power delivered. Okay, so the power input at the input point supposedly P equal to V, in this case V1 squared, sorry, V1 over 2 RMS divided by the impedance of the lines. Alright, so we can call this as P in or P1. So what happened to P2 and P3? So P2 and P3 receive half of V1. Okay, half of V1. So how much power is received is only 1/4 of the power being delivered to port 2 and port 3. So the total loss at port 2 and port 3 equal to half. Okay, so half power, only half of the power supplied, and half of it being dissipated or lost by through the resistors, right? So the system require higher input power to ensure that higher power can be delivered to the output due to the losses within the resistor itself. Alright, so we have seen that there's shortcoming or there's disadvantages of the T-junction and also resistive power divider. So for lossless two-way divider, first for T-junction it cannot be matched simultaneously. If you use the resistive power divider, it can provide matching, good matching for all ports. However, it provides full isolation and also significant power loss within the transmission line itself. Right, therefore, to improve further, there's an improved version of the power divider introduced into the system, which is known as Wilkinson power divider. Okay, so I'll discuss this in the next lecture.